So we're finally get to do our first inferential statistical test called the one sample t-test. Recall that when I introduced null hypothesis testing procedures, there were some different methods. The traditional method, and that relied on a test statistic and whether it fell within a critical region. If it did, then we rejected our null, and if it's outside, we retain our null. This is going to start making sense here as we move into this one sample t-test. We also have the p-value method, rejecting the null if our p-value is below 0.05. We saw this in our Salk vaccine example, and of course we'll fail to reject if it's larger than that. We've also looked at confidence intervals, telling us even a little bit more information than a p-value or even a test statistic. And so we'll continue to look at confidence interval in terms of what it can tell us about our null hypothesis testing specifically. And we'll see that if we have a confidence interval that does not include this null population parameter or null value, then we're going to say it's different from that. We'll build on this as we go into two sample t-tests, that if two confidence intervals, like for control and treatment, don't overlap, we're often going to see that that means they're significantly different. So all of these go hand in hand, and we're going to see they're all mathematically related. And so often, if I get a low p-value, I should have a test statistic that falls within a critical region. And if it's a one sample t-test, my null value is probably not going to be in my 95% confidence interval. So I also introduced this general procedures, what do you do first, and a list of things we've got to do. And I've added on to that just to really flesh this out. We should have a well-defined research question. We want to know what it is we're trying to look at. Is there a difference between these groups? And in a one sample t-test, if I sample my population, should it be different from some null value I have? When we have a well-defined research question, when we know what it is we're after, then we can create a good experimental design. And with that, we'll state our null and alternative hypothesis. And of course, remember in this procedure, we're statistically testing the null hypothesis and finding support for or not support for the null hypothesis. But we're never going to say that the null hypothesis is true. We don't know that. We never prove anything. We're going to choose a statistical test, and that's going to come with a sampling distribution. We're going to set our alpha level. Of course, we like 0.05. We'll gather the data. Then we'll calculate our test statistic. We'll take that test statistic to our sampling distribution that represents really our null sampling distribution and look to see if it's in a critical region. And we'll also, with that, look to see what is the probability of getting that value under the null. If we get a small p-value and if we get a test statistic in our critical region, we're going to reject our null hypothesis in favor of our alternative. And of course, the opposite is true. If we get a high p-value and a test statistic in our critical region, we're going to fail to reject our null. Of course, that doesn't mean the null is true. It just means we're going to fail to reject it. It's still a possibility. With that, as we saw before, we'll examine those 95% confidence intervals. They give us a lot more information than even a p-value or a test statistic can give us in terms of effect size, as we saw. And we're going to keep looking at these confidence intervals in our statistical tests because they continue to give us more information, and we'll see some relationship between these confidence intervals and our null hypothesis testing. So finally then, we get to make some conclusion about what it is we were trying to answer in our research question. We're using parametric statistics here. So we know we want to get a probability of getting our result under chance, under the null hypothesis if it's no true. So we're saying, oh, I get this result, like in the Salk vaccine, and I want to know what's the probability of getting that by chance alone. We don't really create those null sampling distributions, so we need the theoretical sampling distribution, and we're going to use the t-distribution. It's called parametric because it's defined by two parameters. It is centered on its mean, and the spread of it is the standard error. Thus, it's parametric. Also can be called distribution-based statistics. And that allows us to then get our test statistic and associated p-value and make conclusions. We've seen the t-distribution before. It's called student's t because when it was first put in the literature, the author called himself student. Okay, and again, centered on the mean. The width is dependent on the degrees of freedom. So we know there's more than one t-distribution. And it depends on the sample size and thus the degrees of freedom, n minus 1. And the width of that distribution is also defined by standard error of the mean. We use that t-distribution to create 95% confidence interval with small sample sizes, and that was really to show that there's uncertainty in our estimate and the precision of our estimate. It widened our 95% confidence interval with low sample size. That way we didn't overestimate that precision of our estimate. So now we finally get to use this distribution, or this set of distributions, depending on what our sample size is, for hypothesis testing. And as I mentioned, this is when we don't know sigma. We don't know the true population parameter called the standard deviation. If we knew that, we could use z, but we don't do that here because we don't know sigma. Okay, here's a nice curve demonstrating what it is we're sort of looking for. In between the two tails there in red, you can see that's a retention region. We're going to have high p-values in there, and if our test statistic falls within that area, we're in a retention region. We're going to fail to reject our null. The rejection region really is set by our alpha, and that alpha will also decide what those critical values are, and don't worry, we'll see this. And so if we have p-values outside here in the red region and or test statistics in those regions, it means we're going to reject our null hypothesis. So what we want to do in a one sample t-test is take one sample. I went out and took a sample from one population. I don't have a control and treatment here. I just took one sample, and I want to compare that to some hypothetical population mean or hypothetical null value. Okay, so that's what I'm doing with a one sample t-test. This looks a little like the z calculations we did, but remember, this is very different. What we did with the z is very different. The probabilities were within the table. It's only when we knew sigma, so very, very different. So similar but different. Now, whenever we do a one sample t-test, remember we learned about in normal distributions that we wanted to sometimes make sure that our sample data was normally distributed. And this is why, because it's an assumption. I can't use a t-distribution for my inferential statistic unless I meet these requirements. I've got to have independent observation, and that means that one experimental unit to the next don't influence each other. I had to do random sampling of my population, and I got to make sure my data is normally distributed. So these are important things we want to make sure we have. Now, the independent observations and random sampling, we take care of that in experimental design. We have to test for the normally distributed, and we saw that through our probability plots, looking at those dots, making sure that they were lining up within the confidence interval on that graph, on the percentile or quantile plot, and getting our AD test statistic and its p-value. So we'll continue to do this. So here is a sample that I took of body temperature of human beings. And so I went and measured 35 individuals, and I wanted to make sure, I wanted to do a one sample t-test of this data. And so I wanted to make sure that my data was normally distributed. And you can see here, my dots for all intents and purposes, other than that one, are within the 95% confidence interval, and I have a high p-value above 0.05. Hence, my goodness of fit, my data fits a normal distribution. So what I'm really after here is, hey, I measured these people's body temperature. My research question is body temperature really 98.6? Is that what we always should be having if we're not sick? Okay, so I went ahead and measured these people, and I've got an average from my sample data, a mean of 98.9 with a standard deviation of 2.68. Well, it's not exactly 98.6, but is it different than 98.6 from a statistical sense? Is this just random sampling variation? Because we know that anytime we go in and randomly sample a population, we're going to get a slightly different mean. So it not landing exactly on 98.6 might not surprise us. So, but we want to statistically test that. Okay? So we imagine a null distribution with a mean of 98.6 from which our sample data was drawn. So we want to know what's the probability of getting this different mean of 98.9. So we're going to use the t-distribution. And the chart on the right is simply our, notice frequency there, so it's our sample frequency distribution. So here's the one sample t-test. So our null in a one sample is, we're saying that the mean, and I used mu here, I could also use x bar, but we say that the sample mean, or our mean, is the same of 98.6, not different. So 98.6 for us here is the null value. Now sometimes that null value might be 0. It can be many things. You have to know what you're working with to know what it is your null value should be in a one sample t-test. The alternative is it's not 98.6. So we're going to use a one sample t and ask what's the probability of observing 98.9 with a sample size of 25 when the body temp is really 98.6. So we need to calculate our test statistic. We know we wanted to employ the one sample t-test. Of course, we've already set our alpha at 0.05, and we've collected this data, and now we need to calculate our test statistic. Okay, so this is where it looks like the Z. The difference is, number one, this is in standard error units. So now we're saying with this t-value, what our sample mean and its difference from our null hypothesized value in standard error units. And then we're going to take that and say, does that test statistic fall within a critical region, and is it associated with a high or low probability? Okay? So here we are putting in our information, 98.9 minus 98.6 divided by our sample standard deviation, which is divided by the square root of our sample size. So here's our test statistic. T equals 0.56. So what that means is our sample mean is 0.56 standard errors above the hypothetical population mean of 98.6. Ask yourself, do you think that's going to be statistically significant? Well, let's see. one of the first things we want to do is go back to our t-table, because we need to know what our critical values are in this distribution where n minus 1, so 24 degrees of freedom. So if you look at the curve to the right, I'm saying what's our critical value? That's t with the asterisk. And of course it's plus or minus because we're two-tailed. And so we want to know where those fall in our on our distribution, our null sampling distribution. Now, because it's guided by what we said as our alpha, we'll start to see this relationship even more clearly. So we're looking at area in two tails, 0.05. So we follow down on that area to degrees of freedom 24. So our T critical value is plus or minus 2.064. Okay, so one of the first, we're getting two pieces of information. So I'm going to go back to the p-value now. I have a t test statistic of 0.56, and now I get a p-value associated with that test statistic. And if you look at it, the p-value is 0.58. So there's a 58% chance of obtaining this difference by chance alone. So you shouldn't be surprised, right? You shouldn't be surprised. Why? Not getting above 2 standard errors. Remember that 95% confidence interval? It should all be making sense that we're not far enough away in standard error units to probably be associated with a low probability value. So we can see it here. We are definitely have a high probability. And so at that point, we're thinking, hey, we're going to not reject our null. We're going to retain our null. Fail to reject our null here. Let's keep going on this. Another piece of information is that traditional method, the rejection and retention regions based on that critical value. Okay, look at that critical value. At degrees of freedom of 24, we need to be more than 2.06 standard error units away from each other to get into a rejection region. So, and of course, at those critical values, plus and minus, that represents, in that red region, guess what that represents? Probability values of 0.05 or less, split between the two tails. Okay, so another piece of information that our test statistic is within the retention region, so we're going to retain our null. The final piece of information that we have here is that 95% confidence interval around the mean. So that is actually 97.8 to 100.1. So it's pretty broad, and it also contains our null value of 98.6. So we've got a high p-value, a low t, right? And what I mean by a low t-value, it's lower than our critical value. So low t-value, high p-value, both telling you to retain the null, and a confidence interval that includes our population parameter, our null population parameter, all telling us the same thing. So that confidence interval containing 98.6 means that it's probably not different from 98.6. So they're all pointing to the same conclusion. So our conclusion. Based on this data analysis, we are failing to reject our null hypothesis that body temperature is different from 98.6. Does that mean our null hypothesis is proven? No. Does that mean our null hypothesis must be true? No, it's just still a possible outcome. Okay, and evidence that we used to make this decision, again, we had a low t, lower than our critical, high p, higher than 0.05, and 95% confidence interval that overlaps the null value.